Dames en heren, collega's, familie en vrienden. Wat ontzettend leuk dat u er allemaal bent vandaag. Het is voor mij een bijzondere dag en samen met mijn paranimfen heet ik u van harte welkom. Over enkele minuten begin ik met de verdediging van mijn proefschrift, getiteld Outlier-selection and one-class classification. Oftewel, uitschieterselectie en enkelklasse klassificatie. Voorafgaand aan de verdediging heb ik 10 minuten de gelegenheid gekregen om u wat meer te vertellen over mijn onderzoek. Dit is het zogenaamde lekenpraatje. Ik zal beginnen met een introductie over anomalieën en uitschieters. Daarna vertel ik wat over de probleemstelling en de daarbij behorende onderzoeksvragen. En tot slot presenteer ik de conclusie. Anomalieën spelen een centrale rol in mijn proefschrift. En een anomalie is gedefinieerd als een natuurlijke observatie die afwijkt van wat als normaal wordt beschouwd. 3 voorbeelden van anomalieën zijn een rotte appel, een terroristische aanslag en een vervalst schilderij. Dit zijn natuurlijk 3 totaal verschillende dingen. Wat ze echter gemeen hebben, is dat ze afwijken van wat normaal is. En als ze niet gedetecteerd worden, dan kunnen ze ongezond, gevaarlijk of zelfs duur zijn. Het is daarom zeer belangrijk dat deze anomalieën tijdig worden gedetecteerd. Het is de domeinexpert die vaak verantwoordelijk is voor het detecteren van anomalieën. Voorbeelden van domeinexperts zijn een boer, een luchtverkeersleider of een kunsthistoricus. En deze voorbeelden van domeinexperts horen natuurlijk bij de voorbeelden van de anomalieën die ik zojuist heb gegeven. Helaas zijn er 3 menselijke factoren die het detecteren van anomalieën kunnen belemmeren. Vermoeidheid, wanneer de domeinexpert te lang bezig is. Informatieoverbelasting, wanneer er te veel informatie te verwerken is. En emotionele vooringenomenheid. Denk bijvoorbeeld aan een kunsthistoricus die voor een museum moet bepalen of dat een schilderij authentiek is. De druk die daarbij komt kijken, kan de beoordeling van de kunsthistoricus beïnvloeden. Computers daarentegen kunnen heel lang doorgaan, kunnen ontzettend veel informatie verwerken en hebben geen emoties. Nog niet althans. We zullen eens kijken of de computer die domeinexpert geen handje kan helpen. Omdat een computer alleen met getallen kan werken, moeten we de observaties of objecten, zoals deze appels en sinaasappels, omzetten naar getallen. Dat doen we door bepaalde eigenschappen te meten, in dit geval de breedte en de hoogte. Zo krijgen we een lange lijst van datapunten, wat ook wel een dataverzameling wordt genoemd. Daar kan een computer wat mee. En als we deze dataverzameling visualiseren, dan kunnen wij als mensen ook zien hoe dat voor een computer eruit ziet. En hoe zit dat dan met die anomalieën? Nou, als we de juiste eigenschappen meten, dan kunnen we anomalieën van de echte wereld omzetten naar uitschieters in de computerwereld. En een uitschieter is gedefinieerd als een datapunt dat ver verwijderd is van andere datapunten. Tijd voor een voorbeeld. Stel dat we van een groot aantal vaartuigen de grondsnelheid en de draaisnelheid hebben gemeten. Er is 1 vaartuig dat veel te snel vaart. Dat is abnormaal, oftewel een anomalie. En zoals u ziet, is in dit geval het daarbij behorende datapunt ook ver verwijderd van de andere datapunten. Dus een uitschieter. En als de computer dit datapunt er automatisch uit kan vissen, dan zou die dus in principe de domeinexpert kunnen ondersteunen. Dat brengt ons bij de probleemstelling van mijn proefschrift. En die luidt: in hoeverre kan een uitschieterselectiealgoritme een domeinexpert ondersteunen bij het detecteren van anomalieën? Ik vind dat er aan 3 voorwaarden moet worden voldaan voordat we kunnen spreken van een ondersteuning. Ten eerste moet de domeinexpert weten hoe algoritmen geëvalueerd en vergeleken dienen te worden. Ten tweede moet een domeinexpert 1 of meer effectieve algoritmen tot zijn of haar beschikking hebben. En ten derde moet een domeinexpert weten welk algoritme wanneer gebruikt dient te worden. En deze 3 voorwaarden laten zich vertalen tot 3 onderzoeksvragen, waarvan de eerste luidt: Hoe dienen we de prestaties van uitschietersselectiealgoritmen te evalueren en vergelijken? Nou, het antwoord erop omvat een hoop saaie methodiek en saaie statistiek, dus dat sla ik hier liever over. De tweede onderzoeksvraag is veel leuker. En die luidt: kan er een effectief uitschietersselectiealgoritme worden ontwikkeld dat het concept van affiniteit gebruikt? Nou, ik heb geen tijd om in te gaan op het concept affiniteit, maar het antwoord op deze vraag is ja. Ik heb namelijk een algoritme ontwikkeld dat stochastic outlier-selection heet, oftewel stochastische uitschietersselectie, oftewel SOS. Hier zien jullie 4 keer dezelfde dataverzameling. Die witte puntjes zijn de datapunten. En de kleur op iedere plaats geeft aan in hoeverre een nieuw datapunt daar als een uitschieter zou worden beschouwd. Volgens die 4 algoritmes dus. Rood betekent een hele grote uitschieter. En omdat we zien dat rood vaak ver verwijderd is van de witte datapunten. En de vorm van de kleuren geeft dus aan hoe goed dat een algoritme het doet. De bovenste 2 algoritmes zien er redelijk uit. Maar de onderste 2, die lijken nergens op. En dit zijn de kleuren volgens mijn algoritme SOS. Dat ziet er toch veel beter uit? Nou, de resultaten in hoofdstuk 4 tonen aan dat SOS op bepaalde dataverzamelingen significant beter presteert dan de 4 andere algoritmen. En als jullie mij niet geloven, dan is hier het bewijs. Helaas is geen enkel algoritme altijd het beste. Bovenaan deze tabel ziet u 19 verschillende algoritmes naast elkaar staan. En aan de linkerkant van de tabel staan een hoop dataverzamelingen onder elkaar. Een groen vakje betekent dat dit algoritme het goed doet op deze dataset. De tabel is nog veel langer, maar dit geeft al aan dat we voor iedere dataverzameling, dus voor ieder probleem, beter een ander algoritme kunnen gebruiken. De vraag is echter, welk algoritme? Nou, en dit is ook een onderzoeksvraag, de laatste. En deze luidt: in hoeverre kunnen we het enkelklasse geclassificeerde selectieprobleem oplossen met behulp van een metaleeraanpak? U hoeft het niet om te houden. Met andere woorden, kunnen we voor een bepaalde dataverzameling voorspellen welk algoritme we het beste kunnen gebruiken? De resultaten in hoofdstuk 5 en 6 tonen aan dat we met behulp van de eigenschappen van de dataverzamelingen een model kunnen leren waarmee we redelijk kunnen voorspellen welk algoritme we het beste kunnen gebruiken. Dat waren de 3 onderzoeksvragen. Laten we even teruggaan naar de 3 voorwaarden om het domeinexpert als ondersteunend te beschouwen. Ondersteund. Ten eerste moest een domeinexpert weten hoe algoritmen geëvalueerd en vergeleken dienen te worden. Ten tweede moest een domeinexpert 1 of meerdere effectieve algoritmen tot zijn of haar beschikking hebben. En ten derde moest een domeinexpert weten wanneer welk algoritme gebruikt dient te worden. En met de antwoorden die ik op deze onderzoeksvragen heb geformuleerd, kan ik nu de probleemstelling beantwoorden. En die luidt dat een domeinexpert tot op zekere hoogte kan worden ondersteund door uitschieterselectiealgoritmen in het detecteren van anomalieën. Ik dank u voor uw aandacht. Dat was binnen de tijd. Dan is nu het wachten op de commissie en de corona. En tot die tijd mogen jullie een beetje kletsen. Ja. Nee, hè?
Ik open deze zitting. Mogen de geest van wijsheid en barmhartigheid in ons groeien en tot volle wasdom komen. Gaat u zitten. Ik heet u van harte welkom bij deze academische zitting ter gelegenheid van de openbare verdediging van de studie Outlier-selection and One-Class Classification van Jeroen Janssens. En alvorens te beginnen met het spel van oppositie en verdediging stel ik u eerst graag voor aan de leden van de promotiecommissie. Dat zijn op de eerste plaats de 2 supervisors. Die zitten aan die linkerkant van mij, u zit er daar opzij. Dat is professor Postma van deze universiteit en ook professor van der Herik, ook van Tilburg University. Dan de overige leden die zullen opponeren, die zitten hier achter de tafel. Dat is op de eerste plaats aan mijn rechterhand professor Plaat van Tilburg Universiteit hier. Vervolgens aan mijn linkerhand professor Meijer van de Universiteit van Utrecht. Daarnaast zit dokter Van Zomeren van de Universiteit van Amsterdam. Daar weer naast zit professor Kramer van deze universiteit en de rij wordt afgesloten door professor Lin van deze universiteit. Although the committee and the members of the committee and the candidate are Dutch speaking, we agreed on doing the defense ritual in English. So having introduced to you the members of the committee, I invite the first opponent to open the discussion. Professor Plaat, the floor is yours.
Dear Rector, thank you very much for this opportunity. Dear candidate, dear Jeroen, my congratulations to you for a very fine thesis. It is about algorithms, it is about machine learning, it is about classification, and it looks beautifully, I must say. Many graphs, many figures, many photos. You have worked very hard on making your work look good, and it shows. Now, after those words, to the content of the work. First, I have a confession to make. Like yourself, I like algorithms too. I like puzzles, I like mathematical challenges, I like algorithms, I like them for the clear reasoning by which they allow us to understand difficult phenomena. So, lucky for you, for that reason I like your thesis a lot. Now, as a fellow algorithms person, perhaps unlucky for you, I have a few questions as well. Actually, I have many questions. The rector allows me to ask you a few of them. I would like to start with your main algorithm, SOS, Stochastic Outlier-selection. You have created this algorithm. It's a new algorithm. You have tested it extensively on diverse test beds, on diverse test sets, and found that it outperforms all other algorithms. So you have created a new best algorithm, best in its class, which is quite remarkable. Now my question is, how was this algorithm created? How did it come about? I have a sequence of questions, the first of which is, what was the problem that prompted you to look for this algorithm? And the second question is, what inspired you to come up with this approach? Please, can you explain to us the concept of affinity, which plays a central role in the stochastic outlier selection algorithm? And I must say, I have a few questions. I found you did not discuss it. Well, you discussed it to some level of detail in your thesis, but still I would like to discuss with you about the concept of affinity.
Highly esteemed opponent, thank you very much for your question and for your kind words. So your question is about my main algorithm, my main chapter, also the chapter I've worked on, I think longest of all the chapters. It's also the one about which I am most proud, so I'm happy that you asked this question. And your question, as I understood, has 3 parts to it, all related. Although I also have to make a little remark. In your question, you mentioned that my algorithm is the best and that it outperforms all algorithms. I'm sorry, but I would just like to say that I need to be humble here, and I can't claim that it outperforms all algorithms. It can be, because there is, of course, the no free lunch theorem, which I discussed extensively in chapters 5 and 6. But you're right, it does outperform the 4 algorithms discussed in chapter 4, local outlier factor, local correlation integral, the Poisson window data description, and the support vector data description. But thank you. But unfortunately, not yet all algorithms. So how was stochastic outlier selection created? How did it come about? And this is an interesting story because the problem that we were trying to solve is outlier selection. My thesis, my research is embedded within the Poseidon project, and there we had the task to detect anomalous vessel trajectories. I took a more agnostic approach and just focused on arbitrary data sets. But then once you have a data set, if you have your data points in a certain space, let's say Euclidean space, because that is the dissimilarity measure I use most often, how do you detect outliers? How do you select those points which are most outlying? And this a very important part in this is capturing the local structure of your data set. There are, of course, already many algorithms out there. And I was researching, I was reading a paper by my then colleague Laurens van der Maten, who developed at the University of Toronto, together with Geoffrey Hinton, the T-distributed stochastic neighbor embedding algorithm. That is a nonlinear dimensionality reduction algorithm which maps a high dimensional space onto a lower dimensional space, very often a 2 or 3 dimensional space. And there it is very important that the local structure of the data set is captured and that this is maintained in the lower mapping. And this is, of course, a similar problem. Also in outlier selection, we have to capture the structure of our algorithm. So that was my main inspiration. What TSNE, short for T-distributed stochastic neighbor embedding, does, it uses the concept of affinity, which I do as well. Almost exactly the same definition of affinity. So affinity is related to binding probabilities. The word also has a meaning here in the real world. If we say that a person has affinity with another, we say that they are somehow close to each other. So this concept of affinity represents closeness or being a neighbor. And neighbors are, again, very important because they define the neighborhood in which a data point lies. And again, this data point may have this neighborhood may have a certain density associated with it. And very often, outlier selection algorithms select those data points which lie in a low density region. But then affinity, more closely. So data points, or SOS defines a data point, defines an outlier as a data point with which the other data points have no affinity with. So you can translate this back to the real world, where if nobody has affinity with a single person, with a particular person, and that person is an outlier. It's a bit sad, but it helps in explaining the concept. So mathematically, the affinity between 2 data points decreases Gaussian-like in our Euclidean space. If you like, I can explain a bit more about why we have chosen the Gaussian.
No, perhaps we have other questions.
Do we? It isn't time yet. Oh. Okay, well then,
Satisfied?
Yes, I am satisfied.
Okay.
Thank
I
you very
invite
much.
Professor Meyer for this first round to continue the discussion, please.
Thank you, Mr. Rector. Dear candidate, also my compliments with your thesis. I enjoyed reading it a lot. And I also thought that the SOS algorithm was very nice. And in general, it was described very intuitively. But at some point, you're a bit quick, I guess. And in view of your answer to the previous question, so I guess you will be pleased to know that I also have a question about the SOS algorithm. So in one of the steps, you talk about the perplexity age. But I really don't understand exactly what it is, because I don't seem even to see a definition of it. Mm-hmm. So could you give me a kind of explanation what perplexity is, what kind of role it plays within the SOS algorithm?
Highly esteemed opponent, thank you for your question and thank you very much for your kind words. Again, I am very pleased indeed that I can talk at length about the stochastic outlier selection algorithm. Of course, I've already given some introduction to this algorithm, so I can be a bit more brief.
Yeah.
So you would like to know a bit more about perplexity.
Yeah.
Now, this concept of perplexity, it's perhaps a bit perplexing. Although I have to admit there is not really any magic to it. Let me see where I can, in my thesis, where I can find the definition so that you may all browse to it for those of you who have brought the thesis. So on page 80, section 4.2.8, adaptive variances via the perplexity parameter. So I have to admit that the explanation of perplexity had been postponed towards the end of that section. Otherwise, I'd fear that the reader would lose the flow of the explanation completely. So it deserves its own subsection. And perplexity is the only parameter to the stochastic outlier selection algorithm. It can be interpreted also as the k in k nearest neighbor, where k stands for the number of neighbors you would like to use in defining your neighborhood. Here it is the same. Perplexity is, in some sense, the number of neighbors you would like to have in your neighborhood. However, since we use binding distributions and the probability of being a neighbor decreases Gaussian-like and is not, as in k nearest neighbor, a binary property, which is, I think, the reason why stochastic outlier selection can handle with varying densities and data perturbations better than k nearest neighbor. We have to come up with a bit more vague explanation of this. So perplexity is also used in the paper by Lawrence van der Maat and Jeffrey Hinton when they explain t-distributed stochastic neighbor embedding. But there they also really skip over this. And I just like you, I was wondering about what is perplexity really. And I tried very hard at going for the original paper describing this term. And it turns out there isn't much to it. It has been used in 1997 by Jelinek et al. To compare two probability distributions with each other. But that is not very related to this. So what I did is I performed experiments to somehow quantify what is perplexity. What do we mean when we say effective number of neighbors? And as it turns out, if you set your perplexity to a certain value, let's say 4.5 as we do throughout chapter 4, then about 90% of no, let's put it differently. If you add up the binding distributions that a certain data point has to its h, where h is the perplexity, h closest neighbor, then they will make up 90% of the probability density of this imaginary Gaussian distribution, and then the other 10% is, of course, in the tail of this Gaussian distribution and is distributed among the other data points. So 90%, and I was satisfied with this answer to know that 90% of of the probability distribution is made up of my H closest neighbors, and I hope that you are too.
Okay, thank you. But in hindsight, do you think that, so you talk already about perplexity on page 66 and 67, while the definition is on 81.
Yes.
Is that a good choice in hindsight? Because in the beginning you don't know anything about it, so you're just guessing.
Yes, well, if I remember correctly, then what we sort of are saying to the reader, what I'm saying, is that bear with me, but the explanation is coming. I agree with you. This was a tough choice, and I think in the beginning I included the explanation of perplexity at the point where it was first discussed. But I noticed that many of the proofreaders of my drafts got lost even more, and I didn't want to sacrifice that. So this is the choice I've made. I think I also refer on page 67 in the last sentence of the top paragraph. I already direct the reader to subsection 4.2. So if they are then already interested in an explanation, a more detailed definition of perplexity, then yes, they have the choice to go to that corresponding subsection.
The next opponent is Dr. van Zomeren.
Thank you. Dear candidate, it was interesting reading your thesis. It is very clearly written. I could follow almost everything without problems. I was a bit surprised to see not any mention of vessels, terrorists and pirates, as we have been discussing in the context of the Poseidon project some years ago. I should also like to focus on the SOS algorithm, which is the main contribution, I think, of the thesis. One concern that I had is that you start from several existing algorithms, the LOF algorithm and the LOCI algorithm. The main issues in these algorithms are the notion of outlier that is, or anomaly that is behind this. So is it do you look at it from a global perspective or locally? And if you take a local perspective, do you look at the density or at the number of data that you are taking into account to make a decision? Is a group of outliers an outlier, or how do you see this? So my question is, your algorithm, your SOS algorithm, is a lot more complicated than the original algorithms. So you start from distance, from Euclidean distance, then you transform it to affinity, and then you transform it into probability, and so it's a lot more complicated. Why? Why do you think that making this algorithm more complicated will make it better?
Highly esteemed opponent, thank you for your question, and thank you for your kind words. So your question has a couple of parts to it, and I will address them in order. So I would first like to say a few words about the omission of vessels and pirates. So as I mentioned earlier, my research was part of the Poseidon project, and this project had as its main industrial partner Thales, and Thales is, of course, deals with the maritime domain, and hence, I don't have to explain this to you. You've been part of the Poseidon project for as long as I am, and maybe even longer. So yes, the maritime domain, that was the problem setting in which we operated. But for many machine learners, of course, data is of the essence. We would like to test out our algorithms or existing algorithms on data. And at the start of the project, And there is, of course, there are many factors that influence this. It was a very large project, many different partners. I believe there were 7 different universities involved, 2 companies, and this was sensitive data as well. So the data I speak of is a large collection of vessel trajectories. So each vessel transmits every few seconds AIS signal that contains information about where the ship is, what it contains, and where it's going through. Now, and of course, I was very excited to use this data, but unfortunately, in the beginning of the project, access was unavailable. And because of that reason, I relied on existing data sets, mainly the UCI machine learning repository, which contains many different many data sets.
I think it was a reasonable decision. I can quite understand and appreciate it.
Yes.
Why do you think that your algorithm is better than the other 2?
Well, first of all, it's the results that speak for themselves. Of course, I like my algorithm more because it is my algorithm, and it has. And I don't think that more complex is by definition better. We all know that applying a simple algorithm such as the k-nearest neighbor classifier, which is a very simple algorithm, or naive Bayes classifier, outperforms complex algorithms very often. Now, but still, I don't think that my algorithm is more complex. I think it's more the level of detail that I use to explain all the underlying concepts and to really take the reader by the hand and explain every little step that is involved. Because if we take a step back from all the equations that are in chapter 4 and we think about what the outlier probability really means, then I can summarize this in one sentence, and I've done it before, but I'm happy to repeat it here, is that an outlier is a data point with which other data points have no affinity with. And this is, of course, conceptually, it even has a relation to the real world, so people can relate to it. And I think it is this concept that actually makes the algorithm very, very simple, in a good way. Of course, once we go deeper into the mathematics, then yes, we have to resort to equations. But there are as many equations involved with the local outlier factor algorithm and the local correlation algorithm. And I don't even understand, after reading those papers, I don't really understand why some choices were made. And again, I, of course, have tried to explain my choices in here at much greater detail. So, global versus local was also a part of your question. And most algorithms that I've used perform a local density estimation. In fact, it's not really density in a proper probabilistic way. The only algorithm that does this is the Parson window data description algorithm, which is based on the Parson window algorithm. And this algorithm estimates a global density. It normalizes all the Gaussians added together by each individual data point. It normalizes this so that we have a proper distribution. However, also Parson window data description has been shown to perform significantly less than the local density algorithms. So also when we go to human operators or human anomaly detectors, and I think that humans very often also use a local approach. They try to make use of the context of an anomaly, and for that they will very often take a local approach. Of course, they have in the back of their heads rules. They know about rules and certain regulations and what is normal and what is not. So this may be a global understanding of the problem domain. But what matters most is when we go to the maritime domain, is this vessel going to hit the closest other vessel? And the operator isn't really concerned with what happens 50 miles away. So that is why
I'm not sure about what the humans think, because I really don't know. But I think I should stop for this round. I thank you for your answer.
Okay, thank you.
Thank you. The next question, Professor Kramer.
Thank you. Dear candidate, first of all, I too want to congratulate you with finishing your Ph.D. thesis. It addresses an interesting topic, and it does so in a clear and transparent way. And in addition, as Professor Plaat also said, it looks rather beautiful, as I would have expected of you, with efficient use of visualizations throughout. In my question, I want to give you some further opportunity to talk about the stochastic outlier-selection algorithm, or SOS. Mm-hmm. You already described what it is about, and I want to talk about the evaluation of this algorithm. So in chapter 4, you evaluate the performance of SOS against 4 related algorithms on 18 real-world data sets and 7 constructed data sets. And what you show is that SOS really performs impressively well here. If you look at figure 4.16, this is the performance of all the different algorithms on these sets, then basically you see that SOS is always the best performing method on the real-world data sets, although in a few cases the differences with the other algorithms are quite small. So I think what this this chapter quite convincingly shows is that SOS is indeed by far the best performing system in this evaluation. So at first sight, this seems like a counterexample to the no free lunch theorem, which, as you formulated on page 101, it states that no single algorithm can perform uniformly well over all data sets. And chapter 4 seems to suggest that SOS can. Now, in chapters 5 and 6, you present a meta-analysis, a meta-learning study, this time with 19 classifiers, including SOS, and 255 data sets. And what you see in this chapter is that SOS reaches a decent performance, but that there are a number of other algorithms which outperform SOS, including the MST algorithm, which comes out as the best method here. So the question that I want to ask you is, how do you explain that SOS performs really excellent in chapter 4 and merely very good in chapter 6?
Highly esteemed opponent, thank you for your question and thank you for your kind words. Again, I am delighted to talk a little bit more about stochastic outlier selection.
Good.
Although now we reach to a point where we, of course, are dealing here, as you mentioned, contradictory results, or on first sight, at least. So, indeed, stochastic outlier selection has been compared with 4 other algorithms in chapter 4, and with 18 other outlier selection algorithms in chapter 5, or chapter 6 actually. Also, the number of data sets greatly differs. And I think that there is, if I have to be honest, it is about the selection of data sets that were used. This is, of course, very often a challenge for machine learning researchers. They have some algorithm, or they have an improvement of an existing algorithm, and now in the results section they need to convince the reader that their algorithm is actually best. Or when you do a comparison of existing algorithms, you can be a bit more objective, of course. Now, the the no free lunch theorem, which you've just described, still holds. There is no, I cannot claim that stochastic outlier selection is the best algorithm. However, what I hope to convince the reader of in chapter 4 is that there are many algorithms on which stochastic outlier selection performs better than 4 others. 4 is not a lot, and we may even ask ourselves, is 25 data sets or 18 real-world data sets, is that a lot? I moved to 255 in chapters 5 and 6, but again, we can ask ourselves, is that sufficient? Or can we say 1 data set is already sufficient? If we can say that we have here an algorithm and it performs better on this particular problem, it performs better, then yes, as I mentioned in chapter 6, we should choose that algorithm. So this was, of course, every time I've been reading, I was reading a paper about some algorithm. Very often, 6 data sets were used, or 2 other algorithms. This is the practice. This is the way it is done these days. It's not always feasible to apply your algorithm to many different data sets and compare it to many other algorithms because, first of all, you need to have these data sets available. They need to be in a format that you can process them. Secondly, and this is even more difficult, you need to have implementations of these algorithms, and unfortunately, many researchers don't put their implementations online, or even if you ask them for their implementation, they simply ignore you, or they refuse to share their implementation, or they give you some Fortran code which never compiles in your system. So that is the reason why I've only been using 4 algorithms to compare with in chapter 4, and I was lucky to make use of the data description toolbox made by David Tux from the University of Delft, because that MATLAB toolbox includes many other algorithms and many data sets as well. So to summarize, I hope I still have convinced you that SOS is a very good algorithm for many data sets, but still, it is not the best algorithm for every data set because, of course, of no free lunch theorem.
Okay, fair enough. Thank you.
The last opponent in the first round is Professor Lin.
Dear candidate, first of all, I also want to congratulate you with the nice thesis. It's clear and well written. I have learned something new by reading it. In chapter 3, you compared different outlier selection methods used by 2 different research communities, namely the machine learning and the knowledge discovery in databases. You are the first one to compare the method from both fields. You made 3 observations from your experiment and evaluations. In section 3.5.1 on page 55, you discussed the first observation, which says local density estimates outperform global density estimates. It's probably due to large differences in the density. My questions are, will the use of data sets with larger sample size improve the performance of the PWDD, Partial Window Data Description algorithm? And on the same page, you also compared the local outlier, I forgot the F, the LOF algorithm with the LLC, local correlation integral algorithm. And there you say, well, it's unexpected. The multi-scale LLC algorithm performs less than the LOF. And one possible reason could be might contain only one data point in the LOC method. Please elaborate. Yes.
Highly esteemed opponent, thank you for your question, and thank you for your kind words. And thank you for asking a question not about stochastic outlier selection. So we move on to chapter 3, or move back actually, and your question has two parts. And the first part concerns the parson window data description algorithm. And you ask, does the performance of this algorithm increase if we increase the sample size of the data set? And the answer is yes. In this case, contrary to, or not exactly contrary, but it's related to one of my statements in my thesis, which says, let us first focus on good data before we go on to big data. Now, let's assume here that we have indeed good data, and your question now is related to, or concerns, big data. And the parson window data description algorithm works by putting a Gaussian distribution, we use in this thesis a Gaussian kernel, on each data point. And what we wish to do here is we wish to estimate the true underlying data distribution. This Gaussian distribution acts as a sort of smoother, which is also determined by the parameter h, which is, I think I call it the smoothing parameter, but in other literature it's also called the bandwidth of the Gaussian kernel. So I think it is for many experiments that if we increase the sample size, will it then improve on the performance? And I think here in this case it is yes. The question is also, will it then outperform the local outlier factor or the local correlation integral? Because that's maybe more interesting to ask. And for that I have to say, I don't think so. Because there are certain data sets out there that in which it is very important to perform a local estimate, a local density estimation. I have this, I've shown this by using these toy data sets. Actually, I apologize. These toy data sets have only been used in chapter 4 and not in chapter 3. But in chapter 4, I have used toy data sets, and there I have also shown how by slowly decreasing the, or increasing the density of this toy data set, which contains 2 clusters and a ring, by slowly decreasing the space occupied by this second cluster, we will see that the performance of certain algorithms will decrease, and I expect that also the performance of PWDD will also decrease by that. So I hope that answers your the first part of your question. Now to move on to your second to the second part of your question, local outlier factor and local correlation integral, or LOF and Loki. And at some point, I have mentioned that the performance of Loki may be less than LOF, because there might come a point, or that there is only one data point in the neighborhood, and that would then be the data point for which we wish to estimate the density or establish the neighborhood itself, because Loki, as opposed to LOF, includes the original data point in its own neighborhood. So there's always at least one data point. And now the construction of the neighborhoods, both the local and the extended neighborhoods in the local outlier or the local correlation integral algorithm, is defined by a radius. And this, again, differs from the local outlier factor algorithm, which uses k. And when you can be certain that you will always have at least k data points in your neighborhood. So simply, if you make this radius too small, then it may happen that you exclude all the other data points and you end up with a neighborhood in which you are only included yourself.
Okay. We have some time for a second round, and I invite Professor Plaat to open the second round.
Dear candidate, as I was saying, dear candidate, thank you. Professor Kramer asked you a question about the data sets, and Dr. van Zomeren asked you about questions about vessels and about the real-world domains. I would like to talk to you about those two items. Can you, a lot of colleagues asked you questions about stochastic outlier selection. Again, I would like to ask you a question about SOS. Can you give me an intuition for which data sets SOS outperforms the others? And in answering that question, could you perhaps make the step to the real world, because it says in your thesis, and as Dr. van Zomeren has pointed out, you have worked for a long time on the Poseidon project with vessels and pirates in the real world. You may also, in answering the first question, describe what kind of software did you create, what kind of algorithms did you use and did you create in practice, how did they perform in the real world, and how would you think that stochastic outlier selection would perform in the real world?
Highly esteemed opponent, thank you for your second question. Again, stochastic outlier selection, but then applied to the real world. Or, as I understood, the first part of your question was, can I give you some intuition as to when stochastic outlier selection performs better? And I have to admit that I cannot. So, let me explain. I've been applying stochastic outlier selection and other algorithms to many other data sets. It all started, again, with chapter 4, where I apply SOS on 18 real-world data sets. And I have to admit that I've been very focused on the results themselves, on simply the numbers, and I have never really gone into what do these data sets look like. There are names attached to them. Some are about housing and others are about flowers. But I must say that I have very little knowledge about these data sets myself. I was, of course, interested into when should we apply which algorithm. Otherwise, chapters 5 and 6 wouldn't be there. So, again, to accomplish that, I applied many more algorithms on many more data sets. And I have to admit that the amount of data that brought about almost drowned me. It's a lot of data. We are talking about I think a three-dimensional matrix with 255 rows, 19 columns, and then 3 layers in the third dimension. And that's a lot of data, and there was so much in here, and I have struggled with this meta data set in order to gain some intuition about this. But instead of looking more closely at the specific data sets and the specific algorithms, I focused more on a higher level. And as a machine learner, I wish to apply machine learning to this meta data set. And if my supervisors wouldn't have stopped me, then I would have continued with many more models about this. You can think about constructing decision trees or classification or certain rules that you can derive if data set A, then classifier B. That is, of course, that's not part of this thesis. So, in hindsight, what have we now gained with this meta data set and the meta approach that I've applied to this? I'm not sure. I think if I would have the opportunity to redo this study, then I would have looked more at the...
Ik schors de vergadering voor overleg van de commissie en ik vraag u te wachten tot de commissie terugkeert. Meneer de kandidaat, het college voor promoties van deze universiteit heeft kennis genomen van het door u bewerkte proefschrift. En gehoord uw verdediging heeft het college van promoties besloten u het doctoraat te verlenen. De hoogleraar van de Herik is gemachtigd u op de gebruikelijke wijze met deze waardigheid te bekleden.
Volgaarne aanvaard ik de taak mij door de rector magnificus van de universiteit opgedragen. Uit kracht dan van de bevoegdheid ons bij de wet en bij de reglementen der universiteit verleend, volgens het besluit van het college voor promoties van Tilburg University, verklaar ik bij deze u, Jeroen Hendrikus Marinus Janssens, te bevorderen tot dokter en u alle rechten te verlenen die door wet of gewoonte aan het doctoraat zijn of zullen worden verbonden. Ten bewijze hiervan stel ik u de oorkonde door rector en promotores ondertekend en met het zegel der universiteit bevestigd ter hand.
Ik kwijt mij van een aangename taak, zeer geleerde heer, door u ook namens het college voor promoties van deze universiteit met de verworven waardigheid geluk te wensen. Het woord is nu aan de promotor Postma voor het uitspreken van zijn laudatio.
Dr. Janssens, met 3 S'en. Beste Jeroen, van harte gefeliciteerd met de zojuist verworven waardigheid. Graag feliciteren wij als promotores ook je vrouw Esther, de aanwezige familie en schoonfamilie en je vrienden en collega's. Deze promotie is een prachtige afronding van een meer dan 4 jaar durende ontdekkingsreis, waarbij jij vele delen van de wereld hebt gezien en vele delen van de wereld jou hebben gezien. Ik noem 6 locaties die een belangrijke rol hebben gespeeld in je Poseidon-avontuur. Maastricht, Eindhoven, Tilburg, Hengelo, Cambridge en New York. In het kader van het door het Embedded Systems Institute, EASY en Thales geïnitieerde valorisatieproject Poseidon onderzocht je outliers en anomalieën. Het project draaide om de automatische detectie van verdachte schepen of scheepsbewegingen uit grote verzamelingen van digitale gegevens over de posities van schepen en andere aanvullende informatie. Intelligente technieken, in het bijzondere machine learning technieken, zouden behulpzaam kunnen zijn bij het tijdig detecteren van terroristische aanslagen en andere rampen. Je enthousiasme voor het onderzoek in de machine learning vormde de motor voor het prachtige proefschrift dat je hebt geschreven. Datzelfde enthousiasme maakte ook indruk bij Thales, alwaar je eerst de eenvoudige maar zeer indrukwekkende demonstratie zijn diepe sporen naliet. Het toonde maar weer eens aan dat een demonstratie niet ingewikkeld behoeft te zijn om zijn doel te bereiken. Ongetwijfeld is de belangrijkste bijdrage van je proefschrift de Stochastic Outlier-selection, SOS-methode. Hij is vaak aan bod geweest. Een nieuwe methode voor de automatische detectie van outliers. De methode bouwt voort op een formalisme dat je voorganger Laurens van der Maten succesvol gebruikte als basis voor zijn dimensiereductietechniek. Bij de uitwerking van de SOS-methode heb je dankbaar gebruik gemaakt van de expertise die je hebt opgedaan bij je bezoek aan de wereldberoemde onderzoeksgroep van Zubin-Gharamani in Cambridge. Als persoonlijkheid ben je prettig in de omgang en op je best wanneer je een duidelijk doel voor ogen hebt. Je bent een echte doorbijter. Wanneer je eenmaal hebt besloten voor een richting, dan ga je daar helemaal voor. Het promotietraject, het moet gezegd, is niet geheel vlekkeloos verlopen. Net zoals iedere promovendus had je je ups en downs. Daar kwam bij dat het traject werd gekenmerkt door vele veranderingen. Ons onderzoeksteam verhuisde van Maastricht naar Tilburg. Ik was geruime tijd uit de running en het Poseidon-project had een grote dynamiek. Samen met Ildiko, de postdoc op het project, bezochten we regelmatig de Poseidon-vergaderingen. In deze vergaderingen werden prachtige plannen bedacht en grootse vergezichten geschetst. Het viel niet altijd mee om je onderzoek goed richting te geven binnen deze praktische context. Maar ik ben ervan overtuigd dat je veel hebt geleerd van je ervaringen in het Poseidon Adventure. Het bood een unieke blik op de interactie van academische cultuur en de bedrijfscultuur. Ongetwijfeld kunnen de lessen die je geleerd hebt in het Poseidon-project je goed van pas in je huidige werk als data scientist bij Visual Revenue Outbrain in New York. In de laatste fase van je onderzoek dreigde je vast te lopen. Door de snelle en doeltreffende interventie van de tweede promotor, die in de laatste fase tijdelijk je eerste promotor werd, hervond je jezelf en slaagde je erin om je proefschrift af te ronden. Het is een geweldige prestatie dat je naast je drukke werkzaamheden, de verhuizing naar New York, jullie huwelijk en huwelijksfeest, het tot een goed einde hebt weten te brengen. Maar zoals ik al zei, je bent een echte doorbijter. Daarnaast verdient Esther hulde. Zij gaf je alle ruimte om de eindstreep te halen. Terugkijkend op je promotieperiode bewaar ik ondanks de tegenslagen goede herinneringen aan onze avonturen. Samen met Ildiko hebben we het bruisende uitgaansleven van Hengelo ontdekt. En bij een van onze reizen naar Hengelo heb je me kennis laten maken met de culinaire specialiteiten van de Burger King. Het werd mijn eerste en laatste ervaring met de Triple Whopper. Niet lang daarna ben ik vegetariër geworden. In 2009 maakte je samen met Esther een rondreis door Californië. En tijdens jullie bezoek aan San Francisco bleek het hotel waar jullie verbleven pal tegenover het hotel te liggen waar ik met mijn beide zonen verbleef. Dat was wel heel toevallig. Je zou bijna van een anomalie kunnen spreken. Ik kom tot een afronding. Graag bedank ik mede namens de tweede promotor de leden van de beoordelingscommissie en de promotiecommissie. In het bijzonder bedank ik Dr. David Aha van het Naval Research Laboratory in Washington voor zijn gedetailleerde commentaar op het manuscript. Helaas was het voor Dr. Aha niet mogelijk om hier vandaag aanwezig te zijn. Tevens gaat mijn dank uit naar professor Meijer van SIX, van de Universiteit van Utrecht, die mede namens SIX deelnam aan de beoordeling en aan de promotiecommissie. Mijn waardering is groot voor Poseidon-collega Dr. van Zomeren, vanwege zijn bereidheid om zitting te nemen in de promotiecommissie. Ten slotte dank ik de overige leden van de promotiecommissie, professor Kramer, professor Lin en professor Plaat. Dr. Janssens, beste Jeroen, je Promotores feliciteren je nogmaals van harte en zijn verheugd te zien dat je onderzoek bijdraagt aan de ontwikkeling van de AI. We zullen nog veel van je horen vanuit New York en elders en zien uit naar de continuering van onze samenwerking. Ik dank u voor uw aandacht.
Ik ga deze zitting afsluiten. Mag ik u verzoeken te gaan staan? dat wij volstromen met levensadem die ons aanvuurt tot wijsheid en kennis, om te helen wat onheelbaar lijkt, om te halen wat onhaalbaar schijnt. De zitting is gesloten.